Welcome to the second part of section 1.2. We're going to continue our discussion on domain and range, along with a brief overview of piecewise functions. So turn to page 9 of the required modules. Let's start with this example here. Example 2, finding the domain and range from a graph. So we're going to find the domain and the range of each graph below. And for this first example, I'm going to do a little bit of extra writing. Our domain on a graph is generally represented by all the horizontal variables, or the x values, the inputs, the independent variables. So this here is our domain. What you want to do to find the domain from a graph is go along from the smallest to the largest along the x-axis. You notice here I'm still, technically, if I have an input here, I'll have an output on the graph. But if I go here to 0, there is no graph at 0. But once I'm past 0, if I have this as my input, I have an output on my graph, and so on. So I travel along the x-axis and see if there are any spots, any inputs that lead to no outputs. And there is in this case, right here at x equals 0. So our domain, and actually I just realized I need to scroll up a bit. Here we go. Our domain for this example is going to be the set of all x such that x is not equal to 0. And in case you're curious, the graph, or the function that represents this graph, is right here highlighted in yellow. I'm going to unhighlight that since we don't need that now. We could find the domain using the function, but let's stick to using the graph. Next, let's find the range. To look at the range, we're going to do the same thing along the vertical axes. This is our range. And if you notice, we can travel up, 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 and the only output with no input is 0. Here I have an output for this input. Just as if I'm here, I have this output for this input, this output for this x input. So in this case, our range is the same. It's the set of all y, such that y is not equal to 0. The domain and range will not necessarily match for every graph you look at. Let's examine example B, and you'll see a domain and range that are different. So for example B, our function is a parabola, f of x equals x squared. So let's travel along our horizontal axis this way. And if you notice, this arrow here is pointing off in this direction. That means this parabola goes off forever in this direction. So if I'm here, I should have some sort of input. And let's think about why that is algebraically. If I had negative 10 as an input, I'd have an output of positive 100. Now, if we keep going on the positive side of the x-axis, we can keep traveling along this horizontal axis. We will always find an output as well. So if I had, say, positive 12, I'd have an output of 144. So our domain is the set of all x such that, well, let's write this actually in interval notation. This would be easier. Let's just write it from negative infinity to infinity. And now let's remember our range. Our range, we start here as low down on the y-axis and we go up. Notice here I have no inputs that lead to these outputs, but then suddenly at 0 I begin to have inputs. 0 squared is 0. If I want to go here to 4, I can get at it from negative 2 or positive 2. So this tells me that my range is from 0 to infinity. And since 0 squared is 0, this is included and it gets a bracket. Let's look at examples C and D now. Here we are. So for example C, we have f of x equals the square root of x. Along the x-axis, we find our inputs. There are no inputs leading to outputs here. If I say put in a -5, I'm not going to have a valid output in the set of real numbers. So my first valid input is 0. And then this graph, if you notice, keeps going out to infinity. You can take the square root of 100 and get 10. So no matter what our output is, on the positive side, we should have some input. So this goes to infinity, and the 0 is included. Our range here, if you notice, there's no valid outputs below the x-axis, but above the x-axis, we can start from 0 and go all the way to positive infinity. And then finally, we have the cube root of x. As we've already discussed, you can take the cube root of a negative number. So if we had -8 here, this would be -2 as an output. So that tells me that my domain is all real numbers. You can also write this as that boldface R symbol. And our range, similarly, is going to be all real numbers. I know it doesn't look like it's going down in this direction infinitely. It's going down very slowly, just like it's going up very slowly. So with that, please pull out the handout. If you're on the first version of the modules, you need a handout. If you're on version 2 and above, this will already be in your modules. And you're looking at the piecewise function handout. If you receive this as a handout, since it was not in your modules, this page goes between pages 9 and 10 of your modules. If you have version 2 or above, this is already included. So piecewise functions. There we are. A piecewise function has an output that is defined by more than one formula. The absolute value function can be defined in a piecewise manner. We have f of x equals the absolute value of x. And what does this equal? We get just x if x is positive, so greater than or equal to 0, or actually non-negative because 0 is included. And this equals -x if x is less than 0. So let's evaluate. Let's look at example 4 here. Evaluating a piecewise function. So f of 2, well, what does that equal? Which case are we in? 2 is a positive number. So let's look at this rule here. 2 is definitely greater than 0. So we just output 2. Now, what about -3 as an input? Where in this case right here, -3 is less than 0. So we're going to just output -3, which is +3. So if you notice, I took the negative of my input. So -3 to get +3. And that's because -3 is less than 0. So with that, let's move on to the last example, and this would be graphing a piecewise function. So let's graph the following piecewise function on the grid provided. Let's discuss the definition. So g of x equals x squared whenever x is less than -1. Notice it's not ever when it's equal to -1. G of x equals -2 whenever, or if, x is between -1 and +4. And then g of x equals the square root of x if x is greater than or equal to 4. And if you notice, only this last formula includes a condition with an equality. The rest do not, so we're going to have a lot of open dots on this graph. So let's start by drawing our axes. And draw an axis that gives you a reasonable picture. So I know I want to be able to see -1 and +4. So I'm going to draw my axes kind of skewed off over here. And my technology makes my lines perfectly straight. So I would use a ruler at home to make these lines perfectly straight. So here's our x-axis, here's our y-axis. And let's go ahead and label our horizontal and vertical axes. So go ahead and start with these little hash marks. And then we're going to label some numerical values on each. And then I am going to count my horizontal axis by ones and my vertical axis by twos. And that's mostly so that I can get some larger outputs here, since x squared is going to grow fairly large. So I go 2, 4, 6, 8, 10, 12, 14, 16, and then here I have negative 2. This is going to be negative 1, negative 2, negative 3, negative 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I want to take this moment to point out that you can actually scale your horizontal and your vertical axes however you choose, so long as you are consistent with how you've scaled them. And I consistently stayed by twos on the vertical axis, and I'm being consistent by staying by ones, counting by ones on the horizontal axis. Set up a little table here on the side, and here are my inputs of x, and here are my outputs of g of x. So on a table, these inputs are my domain values. These are my range values. I'm going to take a moment to label that. This is an aside. These are the domain, and these are the range. So I'm going to go all the way from negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. And then for reasons it'll become obvious, I'm going to skip all the way from 4 to positive 9. So when x equals negative 4, which part of this definition are we under? Negative 4 is less than negative 1, so we square it. Negative 3 is less than negative 1, so we're in this part of the rule, we square it. And I keep going. Negative 2 is an input, is less than negative 1, so again we square it. Now what about negative 1? Negative 1 is not less than negative 1, it's equal to negative 1. And negative 1 is not greater than negative 1. So this is actually an undefined output, since negative 1 does not fall into either of these categories. What we're going to do when we draw our graph for this section is we're going to have an open dot in a couple places. So let's just draw this portion of the graph. This is the x squared portion of the graph. So I'm going to go over here to negative 4, and that'll take me up to 16, and that gets a dot. Negative 3 here gets a dot at 9. Negative 2 gets a dot at 4. And then at negative 1, if I were to square negative 1, I'd get a positive 1, but it's not included in my piecewise function here. So I'm just going to draw an open dot where that positive 1 should be. So if I were to square negative 1, I would get a positive 1 as an output, and I'm drawing an open dot because it's not included. And now let's connect these dots. And of course, keeping in mind that this is a parabola, so let's make it a little curved here. Parabolas are not quite straight lines. Well, not straight lines near their vertex. Okay, so now let's look at this part, the second definition, when we're between negative 1 and 4. So when we're between negative 1 and 4, our output should always be negative 2. 0 is definitely between -1 and 4, so our output is -2. +1 falls into this case, so does +2, so does +3. So I'm going to go ahead and put a -2 for each of these. What about +4? +4 does not fall here. So I'm going to draw an open dot on my line. So let's go here to 0 is at -2, 1 is at -2, 2 is at -2, and 3 is at -2. And now at 1, I'm going to put an open dot and connect this line all the way through. And I've just covered up my -2. Let me move this down here. There. And now we do need to go all the way to 4 because we can have an input of, say, 3.5 or 3.75. We could even do 3.99, and 3.99 is technically less than 4. Not technically, it is less than 4. So this would give us an output of -2, so we should have an open dot here at 4. So remember, just because these are not included, -1 and +4 are not included in this second definition, doesn't mean we stop here. Keep going until these endpoints and just use open dots there. Finally, let's look at our last inputs of 4 and 9. I purposely chose 4 and 9 because they're perfect squares, and I notice that this third rule is the square root of x. So only perfect squares will have nice outputs. Other values like 4.5, 7, they will have squares, but I really don't want to get a calculator out and try to figure out where exactly some long decimal lies here. So rather than do that, I'm just using nice perfect squares. And you're welcome to do that as well in your own work. So here's 4. What is the square root of 4? It's +2. The square root of 9 is +3. So here at 4, I'm going to go to a +2. And here at 9, I'm going to go up to a +3. And there we go. Let's connect this. And there's the graph of our piecewise function. So that concludes section 1.2.